Our project is on trajectory optimization for continuous contact brachiation along gapped bars. Brachiation is a mode of transportation for primates, which involves swinging with their upper limbs and raising and lowering their center of gravity to generate momentum. Our system is a 3-link model with 2 arms and 1 body, and the robot swings along bars. In this configuration, there is an actuator at the grasp wrist and an actuator at the swing arm shoulder. In this other system that we considered, the actuators are at the swing arm shoulder and the grasp arm shoulder. We had to satisfy the manipulator equation for our system to work, and in specific, we made sure there was a contact Jacobian to account for the forces on the grasp hand from grabbing the middle bar. In addition, we wanted to specify an impulsive collision for when the swing hand grabbed onto the final bar. This occurred when 5Q was less than or equal to 0. We also wanted to make sure that this collision was inelastic, so we made sure that the coefficient of restitution was 0. This was satisfied with equation 2. Some additional constraints we added were to make sure that there was periodicity between the links of our robot, and this was different for the different actuations that we had. In addition, we had to make sure that the velocity of the grasp hand was 0 for all times, so it wouldn't move off the middle bar. Furthermore, we had to use the geometry of the system to make sure that the swing hand had the appropriate end and final positions, start and final positions. In addition, we added a cost on the actuation of the system. In this simulation, we see a swing from a 1 meter to a 1 meter gap. In this simulation, we see a swing from a 1.5 to a 1 meter gap. In this, we see a 1 meter to a 1.5 meter gap. It is interesting how the robot first goes backwards and increases its gravitational energy before making its final swing. And this, we see upside brachiation as upside down walking. Upside down walking has a very high cost in comparison to swinging, which makes sense because it is not what is seen in nature, so it must be less efficient. The double shoulder actuation cost is much lower than the hand and shoulder actuation, which makes sense because in nature, shoulder actuation is the more natural method of brachiation. We also found limit cycles for the hand and shoulder actuation. We can see the position limit cycle on the left and the phase limit cycle for the absolute angle of the blue link on the right. In addition, we found limit cycles for the double shoulder actuation.
We wanted to not only solve the problem of horizontal bars, but also bars of arbitrary slope. So to do this, we changed the model up and made it a little simpler. First of all, we assumed that contact would instantaneously decrease the angular velocity. This enforces a limit cycle. But even if this were not to be what we'd see in nature, the robot could just stop and let the dynamics die out. Additionally, we had one actuator on the hand and one on the shoulder, but otherwise everything is the same as what was shown in the previous model. So the initial and final angles of this robot are fully specified, and they can be computed using the geometry in these diagrams. So for swinging straight, swinging up, and swinging down, there will be 3 diagrams on the right side, the top one being the total force, the middle one being the actuator-specific forces, and the bottom one being the position throughout the time of the trajectory. So for example, in this middle diagram here, looking at the red line, which represents the swinging shoulder, the actuator on the swinging shoulder, you can see that at first there's a positive torque, which is the arm swinging forward, and secondly there's a negative torque to slow it down as it comes into its final position. And this smooth motion is very reminiscent of monkey brachiation. Okay, so swinging down, we can see that the interesting thing to note here would be that the robot is swinging around from the back, and if you imagine swinging down bars, rather than jerking yourself up forward so that you can come in through the left side, you might very well indeed do the same thing as this robot would do. Swinging up, we see the opposite. You swing in from the left, and I think this is what most people would do as they're climbing up bars. One thing to note here is that the torque gets maxed out, and the effort used to swing up increases rapidly, just as you increase the height of the bars by a little bit. And here are all the simulations on one page, just to compare. And we also did a simulation with the double pendulum, which is just changing where the masses are located mostly. And you can see the motions are a little jerkier and probably less reminding of a primate brachiation. So in the future, we have ideas for possible ways to extend this. For example, 5-link systems, creating controllers and analyzing robustness, using ILQR, creating physical system, and adding new constraints. Thank you, that's all.